2, 1. So welcome in projectile motion. A couple of examples for you. So I did a video which introduces this projectile motion, which basically is a breakdown of components into X and Y kind of coordinate systems. So one which is up and down, and the other one which is horizontal. So that is the X. And with that, you can use various kinematic equations to be able to solve for some interesting items. And this is typically introduced kind of in your first physics course that you would have, most likely, possibly in grade 11, but who knows, maybe even in post-secondary. So I'll put up a link up above there to the introduction on projectile motion, where I go into some little detail with an example as well. And here, all I want to be able to do is solve two questions. So here's the first one. So the first question is, if you have an airplane and it's traveling at 250 kilometers an hour, as you can see there on the actual diagram, and it drops off a package, or at least it wants to drop off a package, so that the package actually lands, okay? So as you can see there, so there's a landing pad right here, so maybe it's for food or something else that this package is going to end up with. Now the height, okay, or at least the height above the ground that this airplane is traveling at is going to be 750 meters. And it is moving at this particular speed. And our goal is to be able to find out at what point should it drop this package, okay? So when should it let go so that it does land right here? Now, you would think, ideally if you can hover around, then, you can be right above it, kind of like a helicopter, right? Or the hovers that we have now. And then you can just simply drop it down. But if you're moving at a speed, you have to actually let it go beforehand. And sometimes you have to let it go much earlier, because it will depend on the speed that you're traveling at. 250 kilometers an hour is not super fast for an airplane. So this is more of an airplane which kind of has slowed down probably. However, okay, it's still fast enough that you have to let go a certain distance beforehand. Okay, so that it does land exactly where you want. So we're going to be neglecting resistance, and this of course is a common theme in projectile motion, especially when you're just being introduced. So there's no, you're basically in a vacuum, so it's not really an accurate depiction of the problem. However, it gives us a good sense in how to start apply the various questions we might want to be able to ask. All right, so let's go ahead and try to solve for this distance. How far away should we actually drop the package? So how would we kind of break this down? Well, so one of the things that you should always think about, there are always two components, right, that you're thinking of. There's a vertical component, which is the Y component that you have in there. And you can treat that separately from the horizontal component, which is the X component. And that's actually what we're trying to find, at least the distance. So now, on the vertical component, we actually know quite a bit. So what do we know? And it's worthwhile for us to be able to write all of these things down. So first of all, there's always gravity, which acts on any packages or anything that is thrown up or down. So we do have, okay, in that direction. So I'm going to just call gravity in here, so G, and we'll assume that it's 9.8, meters per second squared. And in this case, it will be actually down, right? So it's being pushed down. Okay, at least that's how gravity is pulling these items down. Now, what else do we know? Well, we certainly know the distance, right? So we know the actual vertical distance. Okay, so the change overall in the distance, okay, what it would be. Now, this will depend on how you refer to this, right? So what the reference is, keep in mind that the displacement, so that distance, okay, it is 750 meters, but is it going to be positive or negative? It will depend on how you actually write these down. So, don't forget, so, if you write the final minus the initial, which I will, I guess, write, this is just for the Y, well, and I will assume that up is positive for us, and let's say the ground is 0. So that means the final destination, right, would be at 0 meters, okay, and then the initial destination, or at least the initial distance would be, or position for us, I guess we can put a position vector in there, is 750 meters above the ground. So that means this would have been negative 750 meters. Now, do you have to show all of that? Not necessarily. You know, most of the time, you might just simply write that the actual y component is 750 meters if you were just doing y component, and then 0 would be at that point. So either or, it doesn't matter. But then you have to be consistent with your gravity as well. All right. So which one you use is up to you. Okay. Just be consistent. So I'm going to stick, okay, with my reference point of up being positive. So that means I need the negative 9.8 for gravity, which is pulling it down. And then the displacement would indeed be negative 750 meters because that's what it was displaced with respect to the reference, which is 0, the ground. So now what else is actually given? So, you know, we typically want to be able to know what the initial velocity is. And this initial velocity in here, so notice that it is moving horizontally, this plane. So if it's moving horizontally, so the angle of it is 0, right, with respect to that particular airplane. And if it is 0, so it only has a horizontal component for our actual speed that this thing is moving at. So when you let go of this particular package, it's going to have the same speed as the airplane initially, and it's going to carry throughout because of the fact that we're neglecting any resistance. So it's going to be assuming that it's going to be moving horizontally in the same speed. But the ground, the gravity is going to start pulling it down. So it's going to start to have that projectile motion where it just kind of has that, you know, looping path that we have. But in the vertical direction, it doesn't have any speed initially. So initially, it will start off with 0 meters per second. That's what it will be, right? Because of the fact that it's just moving horizontally. It's not moving at an angle with respect, okay, to the actual airplane. So that's one thing. Now, I will write, so that means that the initial, okay, this is for the x component, and I guess this was for the y component. Okay, so this one is 250, kilometers per hour, and we might have to change that to meters per second to make everything work, but we'll get back to that. So now, with all of this information, now why would I want to be able to write all of this down for myself? Because ultimately, what I'm after is this. That's what I want. So if you think about that, well, what is that, displacement in the x, okay, that I have in here? Well, that particular displacement that I would have is going to be based on the speed the package is moving, and then for how long it has been moving for. So you may recall, so this is going to be, okay, really just your actual speed multiplied by the amount of time that this package is in the air, right? There is no accelerations here, right? Okay, I know we're neglecting any resistances, so really this is the equation that we have. Now, we do have this, right here. It's in kilometers per hour, but we can certainly change it. But we don't have this. We don't know for how long this package is in the air, so we have to find that out. And that information, so this information is going to be found out from the vertical information that you have. Now, how would we find this information? So don't forget that ultimately, okay, what we have is, so that our total displacement, okay, that we would have is equal to, and please recall this information, so this is the equation from kinematics. So this is your initial velocity, okay, that you would have, and this for us it's in the y direction, okay, right there, multiplied by the amount of time plus 1/2 times acceleration, right, delta t squared. So this is what we have. Now you can put the vectors on these as you need, although we understand we're dealing with up and down, so I'm not going to put the vectors there, okay, on it. So this is, so this one obviously is a vector, and then this one is also a vector for the acceleration, okay, that we have because it's downward. But we know that it's down, so I'm going to just put that in. So now substituting all of this. So what is that delta D? Well, my delta D, so this right here, is the negative 750 that we have. That's how it would be displaced, right? Because it's 750 meters. My initial, so this, what I would have right here, this thing, my initial speed is 0. So this is right here. So this term is gone. I don't actually have it because 0 times delta t is still 0. And now I will have 1/2. My acceleration is negative 9.8. And then my delta t, I don't know what this is, but I can certainly now solve for it, right? So now solving this, so this is going to be negative 750. So notice multiplied by 2. So that is this 2. I can multiply both sides by 2. So that will get rid of this. Okay, I will then divide both sides by negative 9.8. So I'm going to have negative 9.8 on both sides. So that's division that I would have. So if I would multiply this by divide by negative 9.8, then this would be canceled and it would just stay here on the right hand side. And then of course I would have my delta t squared. So now with that, well, I can find out what this is exactly. So the negatives cancel, so those are gone. So I have 750 multiplied by 2, which is 1500. And then 1500 divided by 9.8, which is 153, okay, for us. But I have to take the square root of this. Now don't look, so right here I have the square, so that means I'm going to have to take the square root of both sides. So I can take this answer, okay, and take the square root of that. So this is the same thing as taking, okay, the square root in this way. So I have delta t, which is equal to, 12.37179. I'm going to keep these for myself, okay, so keep at least, 4 or 5 decimal places until we have to round, but we'll do that at the end. So now that I have my delta t, well, now it's going to be much simpler. So I have this right here. Now, sure, okay, so I can change this, so I'm going to do that on the side. So 250 kilometers per hour. So let's, change that, I guess, to meters per second so that we would have that. So at least it aligns with the unit. You don't have to necessarily change it, but since this is in seconds right here, so it's about 12 seconds, so I'll just keep it in that. So that means, I can get rid of the kilometers. So I'm going to do that in fast forward fashion in terms of getting rid of this. So that will be so there we have it. All right, so here it is. And now since we have this, I already have it on the calculator, I can multiply it by 12.37179, how many decimal places you kept there. So this is going to be about 859 meters. It said round, I think round to the whole right here, so to the whole number. So I'll just leave it at that. So what does this mean for us? Well, what it means is that if we were flying this airplane, then we would have to let go, okay? Notice 859, that's actually quite a distance, right? So it's almost 900 meters or almost 1 kilometer, so not too far away from that. But we would have to let go of this package, 859 meters, and then it would just on its own will just project out, okay, and then fall through at the desired destination. So that's one example, and this is a nice example which forces you to be able to understand this projectile motion. Here's another example for you. So it's a little bit different, okay, than the previous one. So what do we have in here? So we have, let's say we have a ball and it is being launched, and notice that it's 25 degrees, but it's 25 degrees to the vertical, all right? So that's the angle that it makes, and it's being shot out at 25 meters per second. And as you can see there, so, so it takes on and it has this projectile pathway, right? So it's at a cliff, falls off that cliff, and I guess there's even a gorge there or something like that where it just continues on. Now, notice the information that we have is we know the angle that it's being shot out at. We know the initial speed of that. We don't know what the height here is, but we do know that where it falls, okay, from where it's been shot, is 90 meters away on the horizontal, right? So this is what we have. And now again, you can choose your reference however way you like it. Since we're moving to the left, you can make it negative if necessary. Okay, so that is all up to you. Just be consistent. All right, so I'm going to make them pretty much all positive in this way. So let's see what they're being asked us for. So they say find the maximum height, right? Now, it will have a maximum height because gravity is going to be acting on this. So we know that gravity for this ball as it gets shot out, doesn't matter at what speed, eventually, right? It will go, but it's going to slow down, and eventually it's going to have a speed of 0. And then gravity is going to be pulling it back down. It's going to start to speed up, right? As you're going through, eventually it hits the ground. So how do we find that H max? Okay. Well, for the H max, so that would have been the first thing. Maybe I'll do it right here and hopefully it'll fit. So that's all about verticals. So in the vertical, again, what do we know? We know that gravity, so this is negative 9.8, meters per second squared. So that's, okay, it's kind of pulling it down. So we know that. We know the initial, right? So we know the initial shutout, okay, of this. So this would have been V initial, okay, this is in the Y direction. So we know what this is, okay? So now we have to be careful with the angle here. So I'm going to maybe draw this out. So let's say this is the vertical, this is what it's being shot out at, okay? So I'm going to make my little triangle. So this is 25, right? This angle is 25 degrees. So now I want to know the vertical. I want to know the vertical component, at least for the moment. So that vertical component is it's an adjacent to that angle, right? So this is adjacent. So this piece is adjacent to this angle. So what that will be, it is going to be 25 meters per second multiplied, well, adjacent, that means cos, of 25. And I will have exactly on what that is. So let's work that out. So 25 multiplied by cos of 25. And that's going to be approximately 22.657, 69, etc. meters per second upwards. All right, so let's assume that that is, up is positive there. Okay, fine. So now what I will use is I will use the definition, okay, for the acceleration. So my average acceleration, okay, that I would have is nothing else but the change in velocity divided by my change in time, right? So this is what I have in here. And from there, so since I'm running out of space here for the moment, so if I take this, I'm going to bring it down for us. So what do we have? Well, we have all of these. We know the acceleration, which is negative 9.8 meters per second squared down. It's all in meters and seconds here, so there's no worry. So I'll drop the units for the moment. Then I have, and now please don't forget, this is final minus initial, right? Divided by the change in time. But what does this equal? My final is 0 because at the peak, any projectile eventually is going to stop. But that's the peak height, and then it's going to start coming down. My initial one, so that was the 25 times cos of 25 degrees. And I guess since I worked it out, I guess I'll keep it. So this is 22.657, okay, 69, etc. And this is divided by, and then the delta t that I have in there. Now, I don't know what this exactly is, right? Now, why am I trying to find it? Because they're just asking me for the height. Right? So what is that height? Well, in order to find the height, I would, so please note that if you're thinking about the vertical component, so the y component, and you're trying to find the height, you want to find the displacement with respect to the initial, right, velocity that it's being shot out at, which is going to be times delta t plus 1/2 the acceleration, delta t squared. I'm avoiding the vectors again here. But here I have this, right? I have this. I don't have this. And I'm trying to find the maximum height possible. But the maximum height happens when your final velocity, okay, or at least the velocity at the peak height is 0. So this is, okay, the velocity at peak height. That's what this is. That's why I am trying to solve this first, because once I solve for delta t, I can substitute it in here. This is just now an equation where it will tell me what that displacement is at that peak. And that's important, right? That's something that we want to be able to do. So from here, so what we have, I'm going to shift this out of the way, okay, put it down here, and I'm going to manipulate our equation that we have in here. So this is going to be delta t is equal to, the 0 makes it very simple, so it's going to be negative 22.65, 769 divided by negative 9.8. So that gives me the peak time. Well, this is already answered in here, or at least entered. So divided by 9.8 because the negatives cancel themselves. So this isn't very long. So it's 2.312 seconds approximately. Now that I have that, I can substitute it back into here. So from here, well, I have my initial. So this is going to be 22.65769. Again, enter as many as you like. But I'm going to round at the end, so I like to keep, 4 or 5 decimal places. I have this, which is 2.312. Okay, now this is going to be plus, 1/2, negative 9.8. And then, again, I'm going to substitute the time, okay, and square it. So let's plug all of this back in here. So 22.65769 multiplied by the time, so 2.312. Then it's going to be minus, so minus right there. Okay, that's that minus. It's going to come out to the front right here. And I have a half, which is 0.5, multiplied by 9.8, and then multiplied by 2 and this is 312 squared. And I'm going to just close the bracket. So this equals 2, and this is 26.19239, etc. It said round to the 2 significant figures. So 2 sig figs would be about 26 meters. So it's going to get, launched up 26 meters up high. That's going to be the peak. And then it's going to start to come down. So once we have this information, right, well, then we can actually jot it down in here. And this would have been our peak, right? So this is going to be the peak from here to here. All right. Now, what else do they ask us? Because they ask us another question. Find h. Okay, and h is all of this, right? So that's the height, okay, above the actual, okay, what we have in terms of from the launch of that ball or whatever it is that has been launched. Now, we know that it has gone up 26 meters up high, right? So now the question is, okay, if I know in here the distance, right, horizontally that this has traveled, which is 90 meters. Now, I know what it has been launched at, okay? So now, if I do this, I'm going to have, so this is part B. So I have my displacement in the x, I'll make it positive, all right? Although I guess technically it's negative, it's to the left. Okay, so, but that's fine. So that is the distance that it has traveled, right? So 90 meters, okay, in the horizontal. So this is 90 meters. All right, that's fine. Now, what I need, okay, is that I know, okay, so from here, as I'm going along, okay, so that 90 meters is the velocity, okay, that I have. Now this velocity, it's that initial velocity of the x, and it is multiplied by now delta t, okay, for the duration of the entire path. So this delta t is not the same as the delta t we found for the maximum height, because now we're not just traveling to the top, right? So this was traveling to the top, but we're also trying to include all of this. So for this, well, if we know that this is 90 meters, well, then that helps us quite a bit, because, so once again, what we have, so if I'm going to draw my triangle, I can find out exactly, so this is 25 meters per second, right? This is 25 degrees. So I can find the horizontal initial speed. I can find this, okay, because I know the angle. Now, what is that equal to? It's 25 multiplied by. Now, please notice this angle is opposite, so that means we have to use sine. So that's going to be sine of 25 degrees, okay, times, okay, this delta t. I'll put a little capital T here for the total duration of that ball being launched. Now, filling all of this in, so this is 90 meters, so I can certainly solve for the total time. So now dividing both sides, so if I divide both sides right here, this is just by this. You can compute this, okay, if you wanted to. So that will get rid of that. That's gone, and that will just leave me the delta t. So here we go. So that's 90 divided by, and this is going to be, I'll put this all in bracket, times, and this is sine of 25 equals, and this is going to be 8.51, 8.3, this is seconds, because everything is in meters and seconds here. So that's the total time. Now, what does that give us, right? Well, what that gives us is, it tells us the actual duration of this ball in the entire projectile motion. So all of this entire path, that path, we now know what the time is. And if we know what the time is, then we can find what the displacement is in the y direction. So that displacement, obviously, it's going to be all the way up and then all the way down. But since it measures displacement, right? So since it measures displacement from that, okay, it's going to take away this piece, and it's only going to give us, this is the displacement in the y. And that's exactly what we wanted to be able to find. So here, if I take this further, so that means now in the y direction, well, my total displacement, okay, in the y, and this is indeed your h, it is going to be equal to your initial speed, right, in the y, delta t, this is going to be this t, so that's going to be that. That's how long it has been. And then plus, 1/2 negative 9.8, okay, as you're going through. And this entire thing, okay, as you have it, and this is going to be times delta t, okay, and it's squared. So what does this equal, right, altogether? Now, we have all of these values in here. So I'm going to just substitute them back in again. Our initial, so that actual speed, so there it is. So that was the initial speed. So I'm going to copy this, bring it down. So that's that. That's this, okay? My total time, so times, okay, so this is my total time. That's times this, okay, so that's that. Now I'm going to just write below it, so that's plus 1/2 negative 9.8, okay, and then we need, okay, this, the time, and we need to square it. And notice that's going to give us the total displacement, right, that we have. Okay, so let's plug it all back in. there we have it. So now it's said to round, I think, to 2 sig figs. Yep, 2 significant figures. All right. So 2 significant figures in there. So this is going to be negative 160 meters. Now, what does the negative mean? The negative means that we are, because you might freak out here, okay, if this was our reference, if this was 0, right, these are the positive values. My H max was positive. And so that all it means is, okay, that it's the displacement with respect to that. So it just means that it's 160 meters below the surface. That's all that it means. So that negative just means that it's down, okay, with respect to the reference. And that is it. So those are great 2 examples which will test you. And if you do understand projectile motion, you're going to be running into these types of examples, I'm sure, at some point. All right, so I hope this was helpful. We'll see you in a future video. Bye, everybody.